Greetings, dear students. This video is part of the Liquid Propellant Rocket Engine Tests course from the Department of Aircraft Engine Theory at Samara University. In this course, you will learn why tests are conducted, how to organize them, what tools are needed to conduct them successfully and safely, how to process the results of an experiment to get the most accurate information, how to get the desired results with the minimum number of tests, and much more. This is the second video, part 2 of the course. Here I will tell you what a measurement is, how it is carried out. Let's start with the definition. A measurement is the experimental determination of a numerical value of a physical quantity in an accepted unit of measurement by using special technical means. An important concept for measurement is the unit of measurement is the value of the physical quantity being measured, which by definition is assigned a numerical value equal to 1. The result of a measurement is the numerical value of the quantity found as the result of its measurement, meaning by comparing it with a unit of measurement. The result of any measurement can be expressed as follows, where A is the physical quantity being measured. This A is the unit of measurement and B is the numerical value of the physical quantity being measured in the units adopted. The following tasks are carried out during measurements. Determine the numerical value of the physical quantity being measured. The evaluation of the error in the measurement of the physical quantity. As the above definition suggests, in order to make a measurement, it is necessary to choose a unit of measurement of a physical quantity and to have special technical means for measurement. In many countries, for example Russia, it is mandatory to use the International System of Units, which defines 7 basic units of physical quantities: length in meters, mass in kilograms, time in seconds, electric current in amperes, thermodynamic temperature in Kelvin, quantity of substance in moles, light intensity in candela. Technical means used in measurements and having standard metrological characteristics are called measuring instruments. The metrological characteristic of measuring instruments is defined as the characteristic of one of the properties of a measuring instrument that affects the result of a measurement or its accuracy. In order to determine the accuracy of measurements, the normalized metrological characteristics of technical means are necessary. The standardized metrological characteristics are metrological characteristics established by normative and technical documents. Measurements are divided into direct, indirect, and joint or cumulative measurements, according to the way the value of the quantity to be measured is obtained. Measurements are divided into equally accurate and unequally accurate according to their accuracy. Measurements are divided into static and dynamic in relation to changes in the quantity being measured. Also, they are divided into single or multiple measurements according to the number of measurements in the series. According to the expression of the measurement result, they are divided into absolute and relative. By metrological purpose, technical and metrological. Direct measurement is a measurement in which the desired value of a physical quantity is obtained directly. Indirect measurement is the determination of the desired value of a physical quantity based on the result of direct measurements of other physical quantities that are punctually related to the desired one. Joint measurements are simultaneous measurements of two or more variables that are not of the same value in order to determine the relationship between them. Cumulative measurements are measurements of several similar quantities taken simultaneously, where the values of the quantities to be found are determined by solving a system of equations derived from the measurements of these quantities in various combinations. Equally accurate, a series of measurements of a quantity carried out with the same accuracy by the same instruments under the same conditions and with the same care. Unequally accurate, a series of measurements of a quantity made with different accuracy instruments and or under different conditions. A single measurement is a measurement taken once. A multiple measurement is a measurement of a physical quantity of the same size, the result of which is obtained from several successful measurements, meaning consisting of a number of single measurements. Static measurement is a measurement of a physical quantity that is assumed, in accordance with a specific measurement task, to be constant over the duration of the measurement. Dynamic measurement is the measurement of a dimensional change in physical quantity. Absolute measurement is a measurement based on the direct measurement of one or more principal quantities and/or the use of values of physical constants. Relative measurement is a measurement of the ratio of a quantity to a same named quantity as a unit, or the measurement of a change in a quantity in relation to a same named quantity taken as a baseline. Metrological measurements can be of two types. Measurements of the highest possible accuracy achievable with the current state of the art. This category includes all high-precision measurements and, above all, reference measurements relating to the highest possible accuracy in reproducing established units of physical quantities. It also includes measurements of physical constants, especially universal constants such as the absolute value of the acceleration of gravity. Verification measurements, where the error of which, with a certain probability, shall not exceed a certain specified value. This category includes measurements carried out by the state control, supervision laboratories for compliance with the requirements of technical regulations, as well as the state of measurement technology and factory measurement laboratories. These measurements guarantee an error in the result with a certain probability not exceeding a predetermined value. Technical measurements in which the error of the result is determined by the characteristics of the measuring instruments. Examples of technical measurements are measurements carried out during the production process in industrial plants, in the service sector, etc. All measurements are based on some physical principle. A measurement principle is a set of physical phenomena on which measurements are based. A measurement method is a combination of the use of measuring instruments and measurement principles. A distinction is made between two main measurement methods: the direct assessment method, the method of comparison with a reference measure. The comparison method is subdivided according to the way the measurement is carried out: zero method, replacement method, the difference or differential method, matching method. By type of solution, methods are divided into contact and non-contact methods. Depending on the measuring tools used in the measuring process, a distinction is made between instrumental, organoleptic, expert, and heuristic. The method of matching consists in comparing the level of a signal that is clearly related to the value of the quantity being studied with the level of the same signal but determined by the appropriate measure. The coincidence of this level of these signals is used to estimate the value of the measured quantity. A contact measurement method is a measurement method based on bringing the sensing element of an instrument into contact with the object to be measured. For example, measurement of the shaft diameter with a measuring clamp, or inspection with a bore and non-bore gauge. Measurement of body temperature with a thermometer. Non-contact measurement is the method of measurement based on the fact that the sensing element of the measuring instrument is not brought into contact with the object to be measured. For example, measurement of the temperature of the external surface of an engine chamber with a pyrometer, measurement of the distance to an object with a radar. The direct estimation method consists in determining the required value from the indicating device of the measurement instrument. The method of comparison with a reference measure consists in comparing the measured value with the value reproduced by the corresponding measure. The comparison can be direct or through other values that are clearly related to the measured value and the value reproduced by the measure. In direct comparison, the method of comparison is also called the method of contrast, and in comparison through other quantities, the method of direct comparison or the method of replacement. The instrumental method is based on the use of special technical means, including automated. The expert method, which is based on the use of data from several specialists, for example, in qualiometry, sport, art, medicine. heuristic methods, which are based on intuition. A widely used method of a pairwise comparison, where measured values are compared with each other in pairs, and then a ranking is made based on the result of this comparison. Organoleptic evaluation methods are based on the use of human senses. The evaluation of the condition of an object can be carried out by element and complex measurements. The element-by-element method is characterized by measuring each parameter of the product individually. For example, eccentricity, ovality, cut of a cylindrical shaft. The complex method is characterized by measuring a total quality factor which is influenced by the individual components. For example, measuring the radial run-out of a cylindrical part, which is influenced by the eccentricity, ovality, etc. Checking the position of the profile on the limit contours, etc., as well as evaluating the surface roughness on the sample visually or by touch. The zero method assumes that the effect of the measured quantity is completely counterbalanced by the effect of the known quantity. An example of the zero method of measurement is measuring a mass using a lever scale. The method of replacement is based on comparison with the measure. The measured quantity is replaced by a known quantity reproduced by the measure, keeping all conditions unchanged, meaning checking the accuracy of a scale by placing alternately the measured mass and weights on different cups of the scale, and on a dial scale by placing weights of 1 kg or 0.5 kg on the weighting platform, and recording the accuracy of the mass indicated on the dial. The advantage of the method is undoubtedly the small measurement error, which is mainly determined by the error of the measure and the dead zone of the instrument, zero indicator. The disadvantage is the need for multivariate measures. In the difference or differential method, there is no full equilibration, and the difference between the compared quantities is evaluated by the measuring instrument. In this case, the value of the measured quantity is determined not only by the value reproduced by the measure, but also by the display of the instrument. The main types of measuring instruments are measures, measuring instruments, measuring transducers, information measuring systems. A measure is a measuring instrument designed to reproduce a physical quantity of a certain size, expressed in accepted units. For example, a weight is a measure of mass, a measuring resistor is a measure of electrical resistance, a ruler is a measure of length, etc. A measuring instrument is a measuring device designed to produce a signal of measurement information in a form that can be directly understood by an observer. Measuring instruments are divided into indicating and registering instruments. In indicating instruments, values are read out on a scale or a digital display. Recording instruments record information in any form or in a memory device. Measuring instruments can perform various transformations of the measured value, its integration in time or another independent variable. A measuring transducer is a measuring instrument designed to produce a measurement signal in a form that is suitable for processing, storage, further conversion or transmission, but not directly perceptible. Depending on their purpose and function, transducers are divided into primary, intermediate, transmission, scale, etc. A primary transducer is a measuring transducer whose input is affected by the measured quantity. These transducers are often called sensors. A sensor is a structurally isolated primary transducer from which the measurement signals are derived. The part of the primary transducer that is directly influenced by the measured quantity is called the sensing element. In recent years, the term sensor has been used to denote a sensing element with a minimum group of transducers. Measuring devices and transducers are named according to the type of the measured quantity: thermometers, thermal converters, manometers, pressure transducers, flow meters, flow rate transducers, etc. A measuring device installation is a combination of functionally integrated measuring instruments and auxiliary devices designed to produce a measurement information signal in a form that can be directly perceived by an observer. Information measuring system, a set of measuring instruments and auxiliary devices interconnected by communication channels and designed to produce a measurement information signal in a form suitable for automatic processing, transmission and/or use in automatic control system. Indicator, a technical aid or substance designed to detect the presence of a physical quantity or the exceeding of a level of its value. For example, the presence or absence of a measurement signal can be indicated by an oscilloscopes. An indicator of the proximity of a signal to zero is called a zero indicator. In chemical reactions, litmus paper or other substances are used as indicators. The indicator is also an audible signal of dangerous situations or loads. A distinction is made according to the form in which the readings are presented. Analog measuring instruments. Digital measuring instruments. Analog measuring instruments are instruments that present information as a continuous function of the quantity being measured. Digital measuring instruments are instruments that present information in the form of individual discrete signals in the digital form. Measuring instruments are divided into three categories according to their purpose. Operational measurement standards, references. Operational measuring instruments are those used for day-to-day measurements. They are divided into laboratory and technical measuring instruments. Laboratory measuring instruments have a high degree of accuracy. Measurement standards are intended for the verification and calibration of work measures, measuring instruments and transducers. Reference standards are designed to reproduce and store units of measurement with the highest accuracy achievable at a given level on scientific and technological development. Measurements are subdivided depending on the requirements for the accuracy of the results into laboratory and technical. Laboratory measurements are more precise and are performed during R&D work, as well as the instruments calibrations. Technical measurements are of relatively low accuracy and are taken to monitor the operation of various devices in day-to-day operation. In general, a measuring instrument consists of a measuring circuit, MC, a measuring instrument, a display unit, and a data logger. Measuring circuit is a set of elements of a measuring instrument, which form a continuous path of a measuring signal of the same physical quantity from input to output. The MC of a measuring system is called a measuring channel. A measuring instrument may include several measuring circuits. The MC is a set of measuring transducers connected in series. The input signal X acts on the sensing element and is subsequently converted in the transducers into the output signal Y, which is supplied to the measuring mechanism. The measuring mechanism of a measuring instrument is a set of elements of the instrument that provide the necessary movement of the pointer, arrow, spot of light, etc. For example, the measuring mechanism of a millivoltmeter consists of a permanent magnet and a moving frame. The display unit of a measuring instrument is a combination of elements of a measuring instrument which provide a visual indication of the values of the measured quantity or of the quantities associated with it. The pointer of a measuring instrument is the part of the display device whose position relative to the scale marks determines the reading of the instrument. For example, an aneroid barometer has a moving pointer. A mercury thermometer has a liquid column surface. The recording device of a measuring instrument is a combination of the elements of a measuring instrument which record the value of the quantity being measured or of the quantity associated with it. This slide shows examples of modern measurement systems using pressure measurement as an example. A primary transducer is installed directly at the point of measurement, which records the measured value and converts it into an output signal. When measuring temperature or flow pressure, for example, their values are often converted into 4 to 20 milliamperes electrical signal. This signal is transmitted through the communication lines to a measuring instrument, which converts the primary signal and transmits it to a display unit, for example a dial indicator or a display, and a data logger. Often, the measuring mechanism indicating and recording equipment is a single unit. The display unit converts the measured signal into a human-readable form. The data logger records the measured signal on a computer or a hard drive in the form of a number or as a graph. A person operating a measuring instrument interacts with a measuring scale. The scale of a measuring instrument is a part of the display unit of a measuring instrument that is an ordered series of marks together with the numbering associated with them. Scales can be marked uniformly or irregularly. For this reason, scales are called uniform or non-uniform. The correctness of this interaction has a strong influence on the accuracy of the measurement, so let's take a look at what a measuring scale consists of. Scale mark is a mark on the scale of measuring instrument, dash, spike, dot, etc., corresponding to a certain value of a physical quantity. The numerical scale mark is a mark on the scale of a measuring instrument at which the number is marked. Scale division is a gap between two adjacent marks on the scale of a measuring instrument. The graduation mark is the difference in value between two adjacent marks on the scale of a measuring instrument. Scale length is the length of a line passing through the centers of all the shortest marks on the scale of a measuring instrument and bounded by the start and end marks. The line can be real or imaginary, curved or straight. The length of the scale is expressed in units of length independently of the units indicated on the scale. The initial scale value is the smallest value of the measured value that can be read off the scale of the measuring instrument. For example, for a medical thermometer, the initial scale value is 34.3 Celsius. The final scale value is the largest value of the measured value that can be read off the scale of the measuring instrument. For example, for a medical thermometer, the final scale value is 42 Celsius. Scoreboard of a digital measuring instrument is a display device of a digital measuring instrument. The error of measurement is understood as a deviation of the measurement result from the true actual value of the physical quantity being measured. The accuracy of a measurement is a quantity that reflects the closeness of the result obtained to the true value of the quantity required. The greater the accuracy of a measurement, the smaller its error. Measurement errors are classified according to the following characteristics. A distinction is made between absolute, relative, and reduced error. Errors are divided into random, systematic, and rough according to their nature. Depending on where it occurs, a distinction is made between instrumental, methodological, and subjective errors. According to the dependence of absolute error on values of the measured quantity, a distinction is made between additive, multiplicative, and nonlinear errors. According to the effect of external conditions, errors are divided into basic and additional. Depending on the influence of the nature of changes in measured quantities, errors are divided into static and dynamic errors. Absolute error of measurement is the error of measurement expressed in units of measured quantity. The difference between the measured value of physical quantity and the actual value of the measured quantity. The absolute error says little about the actual accuracy of the measurement. For example, if an absolute error of 1 Newton was made when measuring the thrust of an engine, the result for an engine with 10 to 5th power Newton thrust should be considered very good, 0.01% relative error. If, on the other hand, an engine with a thrust of 10 Newton is tested, the measurement accuracy cannot be considered high, relative error of 10%. Relative error of measurement is the error of measurement expressed by the ratio of the absolute error of measurement to the actual or measured value of the quantity being measured. Relative error in fractions or percent is found from the ratio, where delta x is absolute error of measurement, x is actual or measured value of the quantity. Measuring devices are often characterized by the reduced error, which is defined as the ratio of the absolute error of the measuring device to the standard value. The upper limit or measuring range of the device is taken as a standard value. The reduced error is usually expressed as a percentage. A random error is an error based on a number of causes, varying randomly from measurement to measurement. The value of random error cannot be determined in every experiment and cannot be influenced. However, a large number of experiments may reveal some regularities common to the type of the error. A systematic error is an error that remains constant or changes in a regular way when repeated experiments are performed. Depending on the source of origin, the following types of systematic errors are distinguished: methodological error, instrumental error, subjective error. A rough error in experiment is an error that is significantly larger than the error justified by the nature and conditions of the experiment and the properties of the measuring instruments used. Rough error can be caused by a malfunction of the computer, a sudden short-term change in the voltage supply to the instrument, a clerical error made by the experimenter when recording the measurement results, or an incorrect reading of the instrument. When readings are taken incorrectly, a rough error is called a lapse. Rough errors can be detected by statistical methods, and results containing rough errors should be excluded from consideration. According to the place of origin, errors are divided into instrumental, methodological, and subjective. Instrumental errors are determined by the accuracy of the measuring instruments used. It is generally accepted to distinguish between basic and additional errors. The basic error of a measuring instrument is the error of the instrument under normal conditions. Normal conditions are those under which the conditions affecting the measuring results, temperature, humidity, pressure, etc., are within the specified range. Additional error is the error caused by the effect of the influences on the measurement when the operating conditions deviate from normal. In some cases, instrumental errors can be eliminated by making corrections. Instrumental errors has a specific meaning when applied to a mathematical experiment performed by means of a computer. The instrument is a computer, and the instrumental error is due to rounding calculations with a large but limited number of significant digits. Methodological errors are due to the approximation of the mathematical description of the phenomenon under study and the possible approximation of their solution methods. Inaccuracy of the ratios describing physical laws and the phenomena on which the measuring principle is based. Possible mismatch of measurement conditions with the conditions for which these ratios were obtained, etc. Methodological errors do not depend on the accuracy of the measuring instruments used in natural and analog experiments. Subjective errors are due to the individual characteristics of the person measuring during the experiment. Subjective errors are caused by a delay or advance in signal registration, incorrect interpolation when readings are taken within one scale division, etc. Improvements in measuring instruments allow this component of error to be reduced or eliminated entirely. With digital instruments, subjective errors disappear. The values of the systematic error component can depend on the value of the measured quantity. For this reason, the terms additive and multiplicative error are used. Additive error refers to the fraction of systematic error that remains constant over the measurement range. Multiplicative error refers to the fraction of the systematic error component that varies with the value of the quantity being measured. For example, for platinum thermal converters of resistance class B, according to GOST R5035-3, the limit of basic tolerable error is plus minus 0.3 plus 0.005 Celsius. Additive component of an error, determined by spread of resistance of thermal converters at temperature 0 Celsius, should not exceed plus minus 0.3 Celsius. and multiplicative component, depending on deviation of sensitivity, should be within plus minus 0.005, summed with additive error. According to the influence of the change in measured values, errors are divided into static and dynamic ones. Static measurement error is the error in the measurement result typical of static measurement conditions. Static measurement is a measurement of a physical quantity assumed to be constant over the duration of a measurement, according to a specific measurement task. Dynamic measurement error is the error in the measurement result typical of dynamic measurement conditions. Dynamic measurement is the measurement of a dimensionally varying physical quantity. All parameters determined during the experiment can be divided into two groups. First, values that are result of direct measurements. These are lengths measured with a ruler, time measured with a stopwatch, mass measured on a scale, etc. And second, values that are determined by calculations and are functions of certain arguments. By a certain transformation of the functional relationship that defines the desired values, it is possible to make that value depend on one or more of the following varieties of parameters. From parameters that can be considered exact, independent variables, numerical coefficients, including such as the number n, the base of the natural logarithm, which can be represented as precisely as possible. From approximate values determined with limited but known accuracy, for example, tabulated data on the thermal or physical-mechanical properties of a substance. From approximate values found as a result of direct measurements, with limited but unknown in advance accuracy. The theory of experimental errors opens up the possibility of solving the following main problems that arise when setting up an experiment. Determination of the error of the direct measurements. Determination of the error of a quantity function given the known errors of its arguments. Such a problem is called a straightforward. Estimating the errors of the arguments if the error of the function is given and the type of functional dependence is known. Such a problem is called an inverse problem. Finding the best experimental conditions under which the error of the function is the smallest. The most important metrological characteristics are measuring range, static characteristic, sensitivity limit of the measuring device or transducer, variation of a measuring instrument or transducer, errors of measuring instruments, dynamic characteristics. First, measuring range of a measuring instrument is the range of values of a quantity within which the acceptable errors of the instrument are limited. The values that limit the measurement range at the bottom and top, left and right, are called the lower limit of measurement or the upper limit of measurement, respectively. Second, within the measuring range, the relationship between the signals at the input X and output Y of the measuring instruments is defined by the relationship Y equals to F from X, which is called the static characteristic of the instruments. In indicating instruments, the static characteristic is fixed by the scale. Therefore, this dependence is also called the scale equation of the instrument. The sensitivity of a measuring instrument is the S value determined by the ratio S equals to limit where delta x tends to 0, delta y divided to delta x equals to dy divided to dx. For measuring transducers, the convergent range plays the same role as the measuring range, and for some varieties of measures, the nominal value of the quantities they reproduce. The calibration characteristic of a measuring instrument is the relationship between the input and output values of the instrument obtained experimentally. The calibration characteristic can be expressed in the form of a formula, graph, or table. The sensitivity threshold is the smallest change in the value of a measured quantity that can produce the smallest detectable change in the readings of a measuring device or the output signal of a transducer. The variation of a measuring in device or transducer is the largest difference in the readings of the device or the largest difference between the output signals of a transducer corresponding to the same value of the input signal, but obtained in one case by a gradual increase and in the other case by a gradual decrease of the value of the quantity being measured. In addition to errors of measuring instruments, we often operate with reduced errors, which are the ratio of the absolute error to the range of measurement, conversion range. For all measuring instruments, the limits of the permissible basic and additional errors shall be fixed. The limit of the permissible basic error is the largest, ignoring the sign, basic error of a measuring instrument at which it will still be recognized as suitable and authorized for use. The limit of permissible additional error is the largest additional error of a measuring instrument at which it will still be accepted as suitable and approved for use. Measuring instruments are assigned accuracy classes, the notation of which coincides with the percent value of the reduced permissible basic error. Accuracy class K is denoted by a number from the following series: K equals to 1, 1.5, 2, 3, 4, 5, 6, multiplied by 10 to the n power, where n equals to 1, 0, -1, -2, etc. The accuracy class of a measuring instrument is a generalized characteristic of that type of instrument, generally reflecting its accuracy level, expressed in terms of the limits of the permissible basic and additional errors, and other characteristics influencing the accuracy. The accuracy class gives an indication of the accuracy limits of a single type of measuring instrument, but is not a direct indication of the accuracy of each individual instrument. This is important when selecting instruments depending on the specified accuracy of the measurement. The accuracy class of a particular type of measuring instrument is specified in the technical specifications, conditions, or in other normative documents. It should be noted that measuring instruments having several measuring ranges may have several accuracy classes. The metrological characteristics of measuring instruments considered allow you to assess their suitability for measuring in quantities under static conditions, when the quantities do not vary over time. In research practice, it is very often necessary to measure values that change over time under dynamic conditions. The results of these measurements are distorted by additional error due to dynamic conditions. This component of error is called dynamic error, and is the difference between the error of the measuring instrument under dynamic conditions and the corresponding error under static conditions. It is due to the inertia of the measuring instrument. This inertia leads to a delay in readings when the instantaneous values of the quantity being measured are recorded. The time constant of a measuring instrument is one of its possible dynamic characteristics. If the signal at the input to the device changes instantaneously by some amount, the output signal may only reach saturation after some time. For example, a hot layer of thermocouple is quickly lowered into boiling water. At the junction on leading wires warm up, the thermocouple thermo-EMF will change, reaching a maximum value after equilibrium has been reached. The relationship of the output signal to time is sometimes expressed as an exponent. Y divided to Y max equals to 1 minus E in the power of minus T divided to tau. By differentiating the last expression, we obtain dy divided to dt equals to Y max divided to tau multiplied to E in the power of minus T divided to tau. By putting T equals to 0, we find the ratio. The value tau included in the above expressions is called the time constant. Its physical meaning is clear from the last formula. If we draw a tangent to the curve y equals to y from t at the starting point, it will reach the value y max after some time equal to tau, the time constant of the device. The smaller the time constant, the less inertial the device is. Low inertial devices are used to study fast variable processes with a high frequency of process variation. I would like to conclude today's lecture with this. In this video, you have learned what measurements are and how they are defined, what measurement instruments are and how they work, what are the errors of measurement. I hope you have understood this lecture. If you have any questions, comments or errors, don't hesitate to let us know in the comments or private messages. We will meet you in the next video lecture.